Hello and welcome to lesson number 27, Permutations and Combinations, part 2. If you haven't watched part 1, click this video in the top right here. In part 1, we discussed all about permutations. We discussed what they are. Therein, we discussed that a permutation is a specific ordering of elements of a given set. We discussed that if you have a set of n total elements and you want to permute all of those elements, as in kind of shuffle them around, that the total number of different shufflings that we could create or permutations that we could create is going to be n factorial, where the factorial function is the product of all positive integers from your number all the way down to 1. We then discussed what permute function is when we considered making subsets of a given function. We discussed that npr or n permute r is a function given by n factorial divided by n minus r factorial, which tells you the total number of different permutations of subsets of length r that can be created from a main set of length n. As in, you take r element from a set of size n, and after taking those r elements you construct a smaller set. You then permute all of the elements in that set and find the total number of permutations that we could create. After solving this, we found that the formula is going to be npr equals n factorial divided by n minus r factorial. What we're going to be discussing in this video is going to be the other half of permutations and combinations, therein combinations. The main difference between permutations and combinations is the ordering. In permutations, we care about the order of each permutation of each individual subset that we create from our original set. As in, if we say npr, what we're talking about is the total number of specific orderings of the total number of specific subsets of length r that we created from a set of length n. In combinations, we don't actually care about the order. We don't care about the order that we select items or the order that they are put in. We instead only consider about the items themselves, as in which elements we choose. So in combinations, what we're really talking about is, instead of the total number of permutations or orderings, we're just talking about the total number of subsets. So in order to establish the connection between permutations and combinations, let's go through a simple operation to create the total number of permutations. In the middle, we'll discover that we've actually also found the different number of combinations for a given set. So let's start off with an example set S, and let's suppose that this set S contains just 4 elements, and they are the elements A, B, C, and D. And what we want to find is the total number of permutations of subsets of this set that have length 2. So in essence, what we're trying to find is 4 permute 2. From our previous definition in the previous video, what we're trying to find is 4p2. So in order to find 4p2, what we would first need to do is consider all the different subsets of length 2 that we could create from this set of length 4. So I'll call all of those subsets by the common symbol S dash. Now remember, S dash is not just one individual subset, it's actually all of the subsets. So if we consider making subsets from this given set, I'm going to write them down and we'll discuss them. They are AB, AC, AD, BC, BD, and CD. These are all the given subsets of length 2 that can be constructed from this original set of length 4. If you try and take a look, you can see that there are no other sets that we could possibly create. If you consider taking any 2 elements, right, let's say B and A, B and A containing set is this set right here. This set right here, A and D, is the A and D containing set. If you choose any 2 elements from this above set here, you can construct all 6 of these subsets. Now then, for each of these subsets, we want to find the total number of permutations in order to find npr. So in each of these sets has 2 elements. For a set of n elements, if we want to permute all n elements as we established prior, it is going to be n factorial. So according to this, there are going to be 2 factorial or 2 different ways that we could permute each of these given sets. So therefore, for each of these sets, there are 2 permutations that we can make. But we have a total of 6 subsets to choose from. So if we consider making all possible permutations of all possible subsets, the answer that we get, which is going to be 4 permute 2, is going to be 2 times 6. Since the total number of permutations of each individual subset is 2 factorial and the total number of subsets is 6, which is going to be 3 factorial. I'm not going to write that for now, but we'll just write the product. It is 12. As we established earlier using our solving of the permute function, we know that this is equal to the number on the top factorial, so 4 factorial divided by n minus r factorial, which is going to be 4 minus 2 factorial. And if you work it out, 4 factorial is 4 times 3 times 2 times 1, which is going to be 4 times 3, which is 12, times 2, which is 24, times 1, which is 24, divided by 4 minus 2 factorial or 2 factorial, which is just 2. So therefore, we have 24 divided by 2, which is in fact 12. Now then, what is the number of combinations within this operation that we've done? Well, according to our definition, the total number of combinations is simply the total number of subsets of length 2 that we could construct from our original set of length 4. So in this case, what we're looking for is the total number of subsets, which is 6. So the total number of combinations in this case is 6. We can actually use this relationship between the permutations and combinations in order to find a specific function for the combinations similar to the function that we had previously for the permutations. In fact, the notation is also quite similar. The combination function, also known as the choose function, is written as NCR, similar to how the permutation function or permute function was written as NPR. NCR turns out to be n factorial divided by n minus r factorial, which is similar to the permute function, but also we have a division factor of r factorial. Let's now observe where this r factorial division factor actually came from. If we consider going from the total number of combinations to the total number of permutations, we can see for each individual combination there are r factorial number of permutations that we could create, where r is the size of our given subset. Because of that, when we are going from combinations to permutations, we need to multiply by r factorial. In this case, we multiplied by 2 factorial. So here we multiplied by 2 factorial. So therefore, if we are going in the reverse direction, we can clearly see how we must divide by that same factor as in r factorial, or in this case 2 factorial, to get back to the total number of combinations. So therefore, we can see how if the total number of permutations NPR was previously found to be n factorial divided by n minus r factorial, that the total number of combinations should be that same number of permutations divided by the total number of permutations of each individual combination that we create, which is r factorial. If you want to see how we could derive the choose function or the combination function in a different way, click this video on the top right here. In that video, I discuss how we can derive the combination function as in choose function using Pascal's triangle. So to get a better understanding of the choose function, let's do a couple of examples. First off, for our first example, let's suppose that we have 10 total students. So we have some classroom where we have 10 total students, which I'm going to label as A, B, C, D, E, F, G, H, I, and J. Here we're assuming that all students are unique from each other. We'll get to how you can have certain duplicate elements and how to handle those later. But for now, let's suppose that all the students that we're considering are unique from each other. Given this, let's suppose we want to choose a set of 3 students out of this total set of 10 students, and by choosing them, we want to ask them to do something special. Let's say we assign them a group project or something like that. So what we are going to consider is the total different number of ways that we could choose those 3 students from this group of 10 students. Now notice, if we are choosing these 3 students from this group of 10 students and we don't really care about the order that we choose them, we just care about which students we choose, what we are thinking about is combinations. So therefore, the choose function is going to be the function that we want. So from this set of 10 students, we want to create subsets that each have 3 students. An example subset could be something like A, E, J. Here notice, these are unordered elements. We just have 3 elements taken from our set of 10 elements. So for the total number of such subsets that we could create based on our equations that we had previously, we know that this is going to be given by n choose r, where n is the initial number of elements in the set, which is 10, and r is the number of elements in the sets that we're going to create, as in the subsets that we're going to create from the original set. So therefore, the total number of different sets that we could create with 3 elements starting from sets that have 10 elements is going to be 10 choose 3, which according to our formula is going to be 10 factorial divided by 3 factorial times n minus r factorial, which is going to be 10 minus 3 factorial. Writing this out, this is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 3 factorial, which is going to be 3 times 2 times 1 multiplied by 10 minus 3 factorial, which is 7 factorial, which is going to be 7 times 6 times 5 times 4 times 3 times 2 times 1. We can see that all of these terms cancel with all of these terms. Simplifying the rest, we can see that this 3 and this 2 cancel with this 9 and this 10, give us another 5 here. So we have 5 times 3 times 8. 5 times 8 is going to be 40, and 40 times 3 is going to be 120. So therefore, 10 choose 3 is 120, meaning that the total number of subsets of 3 students that we will create from our original set of 10 students is going to be a total of 120. For our second example question, let's consider a situation where we have a bunch of chairs and we want to seat people in them. Let's suppose that we have 9 total chairs. So here I'm going to represent chairs with boxes. Here we have 1, 2, 3, 4, 5, 6, 7, 8 and 9 total chairs. And let's suppose in these chairs we want to seat 4 people. So let's suppose we have 4 people and these 4 people needed to be seated in these chairs. Now since we have 9 chairs and 4 people, there will be empty chairs left over once we are done seating the 4 people. What we want to find is the total different number of combinations of seating arrangements that we could have for these 4 people. Now let's just assume for the case of this argument that these 4 people are all non-unique. If they're all non-unique, then we don't need to say person number 1 sits here or person number 2 sits here or anything. We just need to label which chairs are seated on and which chairs are not seated on. In order to identify each of these chairs uniquely, let's number them as 1 to 9. So this chair is going to be chair number 1, this is number 2, this is 3, 4, 5, 6, 7, 8 and 9. Now given this numbering, one possible combination of seatings could be that the first person takes the first chair, this second person takes the second chair, the third person takes the third chair, and the fourth person takes the fourth chair. Here we can see the first 4 chairs get taken in this combination. Another way is for the second chair to be taken, let's say the fourth chair to be taken, the sixth chair to be taken, and the eighth chair to be taken. The question is, how many different such arrangements of seatings are there? Now here again I'm re-emphasizing that each of these people are non-unique. We just want to see whether a person sits or does not sit in a given chair. So in order to bring this into the context of combinations, what I'm going to do is think of this set of chairs as a specific set. And given that set, all we are trying to find is subsets of this set of 9 chairs where we have 4 elements in the subset, and those 4 elements are the 4 chairs where these 4 people sit on. So a potential example of a set for the seating arrangements could be seat number 2 is taken, seat number 5 is taken, seat number 6 is taken, and seat number 8 is taken. So here, if we think of these chair numbers as being elements of a set and then consider all the different subsets that we can create which are of length 4 from this larger set, then we can see that that is exactly the same as finding 4 chairs out of the 9 chairs that we can put people into. So therefore, according to this, what we need to find is the total number of subsets of the set of 9 elements of 9 chairs which have length 4 that we could potentially make from this set. So here we have 9 elements in our original set and we're trying to make sets or subsets rather of 4 elements. So therefore, according to our combination function, our choose function, what we need to find is 9 choose 4. 9 choose 4 will give us the total number of subsets of length 4 that can be created from this original set of length 9. Doing this, we can see that our answer is going to be according to the formula 9 factorial divided by r factorial, which is 4 factorial, times n minus r factorial, which is going to be 9 minus 4 factorial, which is going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 factorial times 5 factorial. Now in this case I'm going to do a little shorthand. I know that 9 factorial is all the numbers from 9 to 1 multiplied together, and I know that 5 factorial is all the numbers from 5 to 1 multiplied together. If I divide these two, then all the numbers from 5 to 1 on the numerator get cancelled by all the numbers 5 to 1 in the denominator. So we can effectively cancel these two and write that 9 factorial divided by 5 factorial is just going to be 9 times 8 times 7 times 6, since all the numbers after that got cancelled. This needs to then be divided by 4 factorial, which is 4 times 3 times 2 times 1. This 2 and this 4 can be cancelled for this 8, and we could cancel this 3 for this 6, leaving us with 2. Now all we have is 9 times 7 times 2, which is going to be, it's easier to do it this way. 14 times 9 is going to be 90 plus 36, which is going to be 126. So therefore the answer here is 126. Meaning that of these 9 seats, if we want 4 people to sit in 4 of the seats, the different numbers of, different sets that we could make where 4 of the seats are taken and the rest are empty is going to be 9 choose 4, which is going to be 126. Now let's expand on this problem by saying that these 4 people here are 4 boys. And let's assume that after these 4 boys are seated, we want to seat 3 girls in the remaining spaces. So now we can see, if we seat 4 boys, there are 126 possible different combinations that we could create from these 9 seats. And in each of those combinations, once we seat the 4 boys, there will be 4 spots that are taken. Let's assume that this is one of them, one of the combinations where 4 spots are taken, and 5 spots will be left over. So we have 5 spots empty, and our task is to seat these 3 girls. So in this case, we have 5 spots and 3 people to sit in them. Once again, we're going to assume that each of these people are non-unique from each other. So we only care about where they sit, not who exactly sits where. So in that case, if we have 5 total elements and we want to make a subset of 3 total elements, once again we can see by the same logic that if we consider these 5 empty seats to be their own set, what we're trying to do is to establish subsets of 3 elements from that set of 5 elements and seat girls in those spaces. So therefore, for each of these 126 combinations that we have for the boys' seatings, we have to find how many combinations there will be for the girls' seatings. So in each of these we have 5 elements, and in each of those 5 elements we are taking 3 elements and making subsets. So therefore the total number of subsets that we could make, given the already simplified subset, is going to be the 5 seats that we have to choose from, choose the 3 people that we need to seat. So we need to choose 3 seats from the total 5 seats. According to the formula, this is going to be 5 factorial divided by 3 factorial times 5 minus 3 factorial, which I'm going to quickly simplify here. I know that 5 factorial divided by 3 factorial is going to be 5 times 4, since all the other numbers cancel out. 5 times 4 is 20. 20 divided by 5 minus 3 factorial is going to be 20 divided by 2 factorial. 2 factorial is 2. So therefore, this is going to equal 20 divided by 2, which is 10. So therefore, given a specific ordering, a specific combination of the boys' seatings, there will be 10 possible orderings of the girls' seatings. So for every single one of these 126 combinations of boys' seatings, there are 10 combinations corresponding of girls' seatings. So by the fundamental theorem of counting, since these two events are independent of each other, since every time we select a certain arrangement for boys' seatings, we get the same number of girls' seatings, we can say that the total number of seatings altogether, the total number of girls' seatings and boys' seatings altogether, is going to be the total number of boys' seatings times the total number of girls' seatings given that the boys are already seated, which is going to be 126 times 10 or 1020. So therefore, total seating arrangements here is 126 combinations of boys' seatings times the 10 combinations for each of those boys' seatings, which is going to give us 1260 different possible seating arrangements. There will be more questions discussed at the end of the video, so if these 2 questions didn't exactly click with you and you didn't exactly understand the answer, you can check those out at the end of the video. Moving on, however, the next thing we're going to talk about is how to handle duplicates in permutations and combinations. Previously, you will recall that when we were talking about NPR and NCR and permutations and combinations in general, we were talking about sets which had no duplicate elements. As in the sample set that we started with, before permuting or before taking combinations of, had all elements being unique from all other elements. This, however, cannot be expected, and in certain cases we could have elements that are duplicates of each other. This is not a property of sets, since a set is defined as the bunch of unique elements that comprise that set. However, we could have starting sets or starting collections where multiple elements are the same element, as in duplicate elements exist. For an example of this, let's suppose the set S is the set that has the elements A, B, C and D. So we can see here we have 6 total elements within this set, but 3 of these elements, the A and the A, are all the same thing. So here we have 3 duplicates. I'm going to call the number of duplicates K for now. I'm going to keep it on the side. I'm going to write K equals 3 for this particular situation. So if we are asked to find the total number of permutations of this set, how do we do it? Well, as we can see, since these A and A are unique, we can perceive that if we naively find 6 factorial and say that 6 factorial is the total number of permutations, we will potentially be overcounting certain permutations. To illustrate this overcounting and to correct for this overcounting, let's assume that these duplicate elements that we are taking into our permutations are actually not duplicates and are actually unique from each other. In order to do this, I'm going to differentiate these 3 A's from each other by labeling one of them as A number 1, the second one is A number 2, and the third is A number 3. Now I have artificially made them unique from each other. So we had 3 duplicates earlier, there were 3 A's, but now I have artificially created them to be 3 different A's. Now if we do this for one particular arrangement, we could have B, A1, A2, A3, C, D. Another particular arrangement would be B, A2, A1, A3, C, D. Another particular arrangement or permutation would be B, A1, A3, A2, C, D. Another arrangement would be B, but this time instead of swapping the A1 and A2, let's swap the A1 and A3. So let's make this A3, A2, A1, C, D. Another one could be B, A3, A1, A2, C, D, and I have missed one. I have missed this one. A2, A3, A1 I have missed. So we have B, A2, A3, A1, C, D. All 6 of these are actually representing the same exact permutation. The reason for that is that if we did not have these artificial handles that I added, these artificial identifiers that separate the 3 A's from each other, all of these would be corresponding to the permutation BAACD. Sorry, actually, I missed one of the A's. BAAACD. So all 6 of these would be corresponding to the same exact permutation BAACD. We can see them as 6 different unique permutations because I have artificially introduced all 3 of these A's to be unique from each other. So then, we've overcounted by a factor of 6. Where is this factor of 6 coming from? It's actually coming from this 3 here. We can see that we have 3 duplicates, and these 3 duplicates, if we consider these 6 permutations which are all corresponding to the same permutation, are actually coming from these 6 different subsets of the 3 A's that have been injected in the middle of this starting B and this CD. So you had the basic pattern B, something in the middle, CD, where that something in the middle is all 6 permutations of A1, A2 and A3. So therefore, our overcounting factor is the number of duplicates factorial. In this case, we have 3 duplicates, K equals 3. So therefore, K factorial is 3 factorial, which is 3 times 2 times 1, which is 6. And here we can see, for this particular permutation B, AAA, CD, we have overcounted 6 total times. This will occur for every single permutation of the set B, CD and AAA. Because of this, if we want to find the total number of permutations of the set where the 3 A's are not unique from each other, what we need to do is to find the total number of permutations for the set when the 3 A's are unique from each other and divide that by the total number of permutations of the 3 A's. So therefore, given the situation where we have n equals the total number of elements, in this case 6, and k equals the total number of duplicates, if we want to permute all of the items, then the total number of permutations is going to be equal to the total number of permutations of the original set, assuming that every element is unique, which is going to be n factorial, divided by the total number of duplicates of the particular element, which is going to be k factorial. In practice, if we have more than one set of duplicates, say we have a second B, so we have another B here, we have B1 and B2. In that case, then we would have to divide by that second overcounting factor as well, because for every set of these B, A, C, Ds, we would have one where we have a B1 and another one where we have a B2. So we have effectively two versions. That 2 is coming from 2 factorial, which is coming from the 2 duplicates of B. So in general, if we have a certain number of duplicates of individual elements, let's say the number of duplicates of the first element is K1, the number of duplicates for the second element is K2, the number of duplicates for the third element is K3, and so on, then our total number of permutations would be the total number of permutations if every single element was unique, as in n factorial, divided by the total number of duplicates of the first element, which is K1 factorial, times K2 factorial, times K3 factorial, multiplying all the way through, and we'll call this last K the K last factorial. So for most sets, most of these K's will be equal to 1, and because of that, most of the stuff on the denominator will be 1 factorials, which is just 1, so they can be removed. The rest of them will be all the genuine duplicates, as in where there's more than one of that given element, which will be divided correctly. So in the case of our simple example here, we have 3 A's, we have 2 B's, we have a C, and we have a D. So in this case, we could think that K1 is equal to 3, corresponding to the A's, K2 is corresponding to the B's and is equal to 2, K3 is equal to 1, corresponding to the C's, and K4 is equal to 1, corresponding to the D's. So in this case, the total number of permutations would be n factorial divided by K1 factorial, which would be 3 factorial, times K2 factorial, which is 2 factorial, times K3 factorial, which is 1 factorial, which is 1, times K4 factorial, which is also going to be 1 factorial, which is going to be 1. So we can see that this generally holds for any set, and for most sets where we have very few duplicates, most of these values of K are in fact equal to 1, which is why they don't appear in our final equation. So this is how you can solve for the permutations of a large set of n total items where we have different numbers K of duplicates of certain elements. K1 is corresponding to the first element's duplicates, K2 corresponding to the second element's duplicates, and so on for all of the elements. For permutations and combinations of subsets, as in when we create subsets of our given set and we permute them, or we just find the different number of subsets, we actually have to get more specific than this. We cannot write general formulae because depending on the subsets we choose, we could have different numbers of duplicates. To illustrate this, let's go back to our earlier example where we had 3 A's, as in A, a B, a C, and a D. Now, given this, let's suppose we want to create subsets of 3 total elements. There are different ways in which we could do this, and I'm going to illustrate one specific criterion which we can use to divide these subsets into different categories. The criterion is going to be the number of A's that we have in our set. So, for the number of A's or number of A's, we could have 4 different values. We could have all 3 A's in our set of 3 different items. We could have 2 different A's in our set of 3 different items. We could have only 1 A in our set of 3 different items. And we could have 0 A's in our set of 3 different items. Each of these cases, as it turns out, needs to be treated differently. So if we consider different subsets of 3 elements that we could create with each of these configurations, we can see that for the case where we have 3 A's, since our total number of elements in the subset that we're creating is also 3, if we have 3 A's, then our subset is the subset A. And there is nothing else within this subset since we have only 3 items to choose from. For our second case, if we have 2 A's inside our subset, then we have A and the third element that we need to choose. For this one, we have degrees of freedom. For the third case, we can see we have 1 A and the other 2 elements can be whatever we want from the remaining ones. Notably, they cannot be any other A's, since if they were any other A's, they would not be belonging to this case. They would be belonging to this case or this case. And for the last one, if we have 0 A's, then that means that we can only consider B, C and D. Since if we have 0 A's, the only other options are B, C and D. So we have B, C and D, and we are forced to choose B, C and D. We could represent this with 3 holes, but we already know that these 3 holes can only be filled with these 3 elements B, C and D. So what we need to do next in this case is to consider every single case and consider the different number of either if we are interested in combinations then combinations, or if we are interested in permutations then permutations. We'll do both of them for this simple example. We'll consider combinations here. I'll represent, we'll see, actually we'll write the whole thing, nations, and over here we'll write permutations. So for the set where we have 3 A's, we have just a single combination, which is the set of 3 A's. And as for permutations, since all of these A's are duplicates of each other, if we do the A1, A2, A3 thing and then divide by the total number of permutations of that set, we're just going to get 1 again. So therefore the total number of permutations of this set is also 1. For the second thing, if we consider the total number of combinations, we could put something here that is any of these 3 elements. So therefore, we could either choose B, C or D to be the third element, and we are forced to have the 2 A's, which means the total number of combinations that we could have for this certain arrangement is going to be 3. As for the total number of permutations, when we shuffle these around, we have 3 total elements. When we shuffle them around, we get 3 factorial, but we have 2 duplicates, which means we need to divide by 2 factorial. Dividing 3 factorial by 2 factorial, we can see it's going to be also equal to 3. This pattern does not continue, by the way, for the rest. This is just a coincidence that we have here. The permutations and combinations for these two happen to be equal to each other. In the next situation, we have 3 total elements of which one of them is chosen for us. We have to choose 2 more, and for these 2 we can only choose from these 3 possible elements. So therefore we have 3 elements to choose from and 2 elements to choose. So the number of total combinations that we have here is going to be 3 choose 2. 3 choose 2 is going to be 3 factorial divided by 2 factorial times 3 minus 2 factorial, which is 1 factorial. So it's going to be 3 factorial divided by 2 factorial, which is going to give us 3. So therefore the total number of combinations in this situation is 3. As for the total number of permutations in this situation, if we have 3 elements which are all unique from each other, since they have to be unique because A, B, C and D are all unique from each other, and A is unique from B, C and D, meaning that the 3 elements that we select here will be unique from each other. If we permute them, all you have to do is take the factorial of those 3 values, which is going to be 3 factorial in this case, which is 6. So therefore the total number of permutations here is 6. As for the last one, for the 3 total choices, we have 3 total things that we can choose from. We have 3 total choices, which means we need to do 3 choose 3. 3 choose 3 is going to be 3 factorial divided by 3 factorial times 0 factorial. 3 factorial divided by 3 factorial is of course 1, and 0 factorial is also 1. So we have 1 overall, which means 3 factorial divided by 3 factorial times 0 factorial is going to be 1. So the number of combinations in this case is just 1. There's only one combination we can choose, and that's the combination of B, C and D. Again, recall, in combinations we don't care about the order, we just care about which elements we choose. As for the total number of permutations, in this set that we are choosing, all 3 elements are unique from each other, meaning that the total number of permutations of the overall set is just going to be that n factorial. So if we have 3 elements, it's going to be 3 factorial, which gives us 6. So therefore, the total number of combinations are these values, and the total number of permutations are these values for these given duplicates. You can see here, when we split these duplications that we choose for our subset into different categories, either having 3 duplicates, 2 duplicates, 1 duplicate or no duplicates at all, we can solve each of those subsets or those individual cases separately using combinations and permutations. So now what we're going to do is to move on to some exam questions from past papers and solve them using these principles that we've learned. So here's our first exam question. It's from the 2018 A-Level Combined Mathematics Paper 1, Part B. It is question number 12A, and it says, a committee of 6 members is to be selected from 2 groups, each having 3 boys and 2 girls. So the groups have 5 total members each. And there's 2 groups, which means we're choosing these 6 people from a total of 10 people. And they say, such that the number of girls in the committee is at most 2. If the number of girls in the committee is at most 2, then it could be 2, it could also be 1, and it could even be 0. It is possible for it to be 0, since in these 2 groups there are 3 boys each, which means there are 6 total boys, which means if we select only boys, we could get the 6 members that we're looking for. So the question is asking us to find the number of different committees that can be formed if, and then the 2 questions. For the first condition, they're saying an even number of members are to be selected from each group. So we have to do all of this stuff, all of this 2 girls and this 3 boys thing to form 6 members from 2 groups, given that the number of girls is at most 2 and also an even number of members are to be selected from each group. So in this kind of question, while the mathematics of permutations and combinations is necessary, another thing that's necessary is logic. How you understand the requirement involved. So let's try and break this down and try and understand the requirement involved and form a mathematical rule that we can use to try to figure out the total number of combinations. To start off, let's take a look at this even number of members are to be selected from each group rule. According to this, from group 1, out of the 5 people, an even number are to be selected, and from group 2, and out of that 5, another even number are to be selected. This total of these two even numbers must be equal to 6, since we are choosing 6 total people. So therefore, we need a pair of two even numbers that add up to 6, and those pairs of even numbers could be the possible numbers of people that we're selecting from group 1 and group 2. Now these numbers of course cannot be negative, since you cannot select negative people from a group. They could be 0 however, but as we'll soon see, that is not going to work here. So let's consider the pairs of even numbers that add up to 6. One pair of even numbers that add up to 6 is 0 and 6. Another pair is 2 and 4. Another pair is 4 and 2. And the last pair is 6 and 0. So here we can see that we could either select 0 people from group 1 and 6 from group 2, or 2 from group 1, 4 from group 2, or 4 from group 1, 2 from group 2, or 6 from group 1 and none from group 2 in order to get our 6 total committee members. There is however a problem with 2 of these options. The problem is that they are impossible. Over here we can see that we have 3 boys and 2 girls in each group, which means we have 5 total people in each group. If we have 5 total people in a group, we cannot possibly select 6 people from that group. So due to this, this option and this option are impossible, since it is not possible to select 6 people from a group of 5 people. So we can eliminate these 2 options and say that there are no combinations where these 2 options are valid. So the only possible combinations are that we select 2 people from group 1 and then 4 from group 2, or we select 4 from group 1 and 2 from group 2. Now that that's out of the way, we know that there are only 2 ways to do this. You could either select 2 people from group 1, or 4 people from group 2, or 4 people from group 1 and 2 from group 2. So here if we start with our tree diagram, like just to get an idea of what's happening, we don't need to do this in the exam by the way, this is just for your conceptual understanding. We can either select 2 people from group 1, which I'm going to represent like this, and therefore 4 people from group 2, or we could select 4 people from group 1 and therefore 2 people from group 2. These are the 2 possibilities. Now given each of these possibilities, to satisfy each of the other conditions required, we need to go into more depth. If we consider the other conditions required, we need 6 total members, which is satisfied by this. We need this even number of members thing, which is also satisfied by this. However, the number of girls in the committee at most 2 is not satisfied by this equation here, this expression here. So therefore we need to go into more depth to try to figure out the total number of girls involved and therefore the total number of combinations. To do this, I've drawn a table here where we're going to consider all the possible combinations of choosing girls and boys. So to start off, if we have to choose girls less than or equal to 2, it means we could either choose 0 in total, 1 in total, or 2 in total. For each of these cases, there are different choices that we could make. Let's first consider choosing 0 girls at all. If we want to choose 0 girls, in the first case that we choose 2 from group 1 and 4 from group 2, to choose 0 girls, we must choose 2 boys from group 1, 0 girls from group 1, 4 boys from group 2, and 0 boys from group 2. However, we cannot choose 4 boys from group 2. The reason we cannot choose 4 boys from group 2 is because, according to this, there are only 3 boys in a group. So that means that this condition is impossible. We can actually erase it. We could write it and write that the number of combinations is 0 as well, but we can erase it because it's not relevant to our question. By a similar vein, for the 0 girls and choosing this case situation, we can see that if we choose 0 girls, to get 4 people from group 1, we would need to have 4 people that are boys. That's also again not possible. Again, if we choose 0 girls, then from the second group we would need 2 boys, which is alright, but from the first group we would need 4 boys, which is impossible. So therefore, this case is also nil, meaning that we cannot choose 0 girls for our committee. It is imperative that we choose at least 1 girl. Now then, moving on to the next case. For one girl, we could choose this one girl from each of the two groups. We could either choose it from the first group or the second group. Now let's go into each of these cases and consider choosing the girl from each of the groups. In the case where we choose 2 from group 1 and 4 from group 2, we could either choose one boy and one girl from group 1, in which case we would be forced to choose no girls from group 2, and then in that case, to get a total of 6, we can see that we would be forced to choose 4 boys from group number 2. So therefore, this situation is impossible. It does not work. So that means that we cannot choose the girl from the group that has only 2 people. Instead, we need to choose the girl from the group that has 4 people. The group that has 4 people, if we choose, we're going to have to choose 2 people from the boys on group 1, 0 from the girls on group 1, and then 3 boys from group 2 and the 1 girl from group 2. Now this condition, unlike all the rest that we've discussed so far, is actually possible. It is possible to select 2 boys from group 1 and no girls from group 1, and it is possible to select 3 boys from group 2 and 1 girl from group 2. So therefore, this is a valid condition, and there is going to be some number of combinations that will apply for this given condition. Moving on, we've established all the cases where we have 2 girls, and so 2 from group 1 and 1 from group 2 from group 1 and 4 from group 2, where we have 1 girl. Let's now go to the case where we have 4 from group 1 and 2 from group 2 and 1 girl. So in this case, once again, the girl cannot be from the smaller group, from the group that has 2 people, because in that case we would need 4 boys from the large group, which is not possible since any group contains only 3 boys. So therefore we can jump right ahead and say that if we are choosing 4 people from group 1, then one of them has to be a girl. So we can choose 3 people, 3 boys from group 1 and 1 girl from group 1, and then we will be forced to choose 2 boys and 0 girls from group 2. This is also a valid combination. You can see this combination is the mirror image of the other combination. That happens because the 2 groups are not separable by anything. Like we cannot distinguish group 1 from group 2. It's just arbitrary naming. Moving on, however, for the case that we choose 2 people, as in this case right here, 2 girls, there are different ways that we could do it. If we want to choose 2 girls, one possibility is that we choose the 2 girls from the smaller set. Another possibility is that we choose one of the girls from the small set and one of the girls from the bigger set. And the last possibility is that we choose the 2 girls from the bigger set. As we will see, however, one of these possibilities is not possible. If we choose the 2 girls from the group that has 2 people, then the other group will have to contribute 4 boys in total. It is impossible for these groups to contribute 4 boys in total since they only have 3 boys in total. So we can already say that we cannot select the 2 girls from the smaller group. Now, the other 2 cases are actually valid. For the case where we select 1 girl from one group and 1 girl from the other group, one of the possible combinations will go from top to bottom, so we'll go from this one first. For the 2 from group 1 and 4 from group 2 case, we would have 1 boy from group 1, 1 girl from group 1, the other girl would be from group 2, and to fill out our total 6, all 3 boys from group 2 would have to come. So therefore, this is one possible combination. The other combination is if we select all 2 girls from group number 2. In which case, we will have to select only boys from group number 1. So group number 1 will be only boys. There will be 2 boys coming, 0 girls. And then from group number 2, we select 2 boys and 2 girls. This again is also valid. It is possible to select 2 boys and 0 girls from group 1. And it's also possible to select 2 boys and 2 girls from group 2. Now that we're done with that, let's consider the case where we're selecting 4 people from group 1 and 2 people from group 2 and selecting 2 girls. In this case, once again, it is not possible for us to select the 2 girls from both from group 2, because if we do that, then we'll be forced to select 4 boys from group 1. Ignoring that case, the other 2 cases where we select 1 from here and 1 from here and both from here are all valid. So considering those 2, for the first case, if we select 1 person, 1 girl from group 1, that means we select 3 boys and 1 girl from group 1, and that means we select 1 boy and 1 girl from group 2. As for the case where both girls come from group 1, we will have 2, 2 and 2, 0. Since we select 2 boys from group 1, 2 girls from group 1 and 2 boys from group 2. So this is all the possible combinations. We've gone through all possible combinations of the total number of girls in the committee, and we've gone through for each of those the different ways that we could select these people in an even number. We could select 2 from group 1 or 4 from group 2, or 4 from group 1 and 2 from group 2. So going through all of that, we found a total of 6 different specific conditions, and for each of these conditions we can find the total number of combinations. Starting off, remember that in each of these groups that we're selecting, there are 5 total members, 3 boys and 2 girls. So if we want to choose 2 boys from group 1, in this case, that means that we need to choose from our total 3 boys, 2 boys. So therefore the total number of combinations for that particular choice is 3 choose 2. It does not matter which 2 boys we choose, the other choices will be unaffected. So therefore the other 3 choices are independent of that first choice, meaning that the fundamental principle of counting applies here, and we can simply multiply the total number of combinations for selecting the 2 boys by all the number of combinations for the rest of them. Going to the next one, to choose 0 girls from 2 girls, the different number of ways is going to be 2 girls choose 0, so 2C0. For the next choice, to choose 3 boys from 3 boys, the total number of ways is going to be 3 choose 3. You can already guess it's going to be 1. And for the last choice, in order to choose 1 girl from 2 girls, we need to do 2 choose 1. So therefore, the total number of overall combinations for this group here, this set of groupings that we have here, for when we have 2 boys from group 1, 0 girls from group 1, 3 boys from group 2, and 1 girl from group 2 is going to be this number here. We can do the same process for the rest of them. If we consider the next one, we need to choose 3 boys from group 1. There are 3 boys in total, that means we need to choose 3 from 3, so 3 choose 3. For the next one, we need to choose 1 girl from group 1. There are 2 girls in group 1, so we have 2 choose 1. For the next choice, we need 2 boys out of 3 from group 2, so that's 3 choose 2. And at last, we need to choose 0 girls from the 2 girls in group 2, so that means we have 2 choose 0. Continuing downwards, the same exact thing for the rest of them. For this choice here, we need to choose 1 boy out of the total 3 and 1 girl out of the total 2, which means we have 3 choose 1 times 2 choose 1. And then here we need to choose 3 boys out of the total available 3 in group 2. So that means we multiply by 3, choose 3, and then multiply by the total number of choices we have. For the girls from group 2, we have 2 girls that we can choose, and we can choose only one of them. So therefore, this is the total number of combinations for this third option. For the fourth option, we can see we have 2, 0, 2, 2. 2 boys out of a total 3 means we have 3 choose 2 multiplied by 0 choices for the girls out of 2. So that means 2 choose 0. For 2 choices out of 3 for the boys, that's 3 choose 2. And for the 2 choices out of 2 for the girls, that's 2 choose 2. For the next one, we have 3 choose 3 for the boys. We have 2 choose 1 for the girls. We have 3 choose 1 for the boys from group 2, and we have 2 choose 1 for the girls from group 2. And finally, we can see we have 3 choose 2 times 2 choose 2 times 3 choose 2 times 2 choose 0, total number of combinations for the last option. So here we can see we have isolated all of the cases and individually found the total number of combinations for each of those cases. Now that we've done this, we can add all of these together to find the total number of combinations overall. To do that, let's take this graph a little bit to this side so that we have a little bit extra space in our table in which we can write our answers. So I'm going to take all of this stuff a little bit to this side. This corner border seems to have not moved correctly, so I'll move that as well slightly to this side. Extend this outward, and now we have enough space to write all the number of combinations. So let's do it. Let's write a bunch of equal signs over here and write out all the different number of combinations for each of these individual options that we could have and add them all together to get the overall total number of combinations that we could have. Starting off at the top, 3 choose 2 is going to be 3 times 2 choose 0, which is going to be 1, so 3 times 1 is 3 times 1 times 2 is going to give us 6. So there's 6 total combinations for this first option. You can verify that the answer is 6 if you substitute the formula of these 4 total choose functions and find their values. It's going to be 6. For the next one, we have 1 option times 2, which is 2, times 3, which is 6, times 1, so that's just 6. For the next one, we have 3 choose 1, which is 3, times 2 choose 1, which is going to be 2, so we have 6, times 1, times 2. So here we have a total of 12 options. For the next one, we have 3 times 1, so 3 times 3, which is 9, times 1, so 9. For the next one, we have 3 choose 3, which is 1, times 2, times 3, so that's 6, times 2, which is going to give us 12. And for the last one, we have 3 choose 2, which is 3, times 2 choose 2, which is 1, so 3, times 3 choose 2, which is 3, times 2 choose 0, which is 1. So we have 3 times 1 times 3 times 1, which is 9. So this is our total number of possible combinations for all of these possible committees that we could produce given the 3 rules that we were assigned. The 3 rules being that the total number of members in the committee needs to be 6, we need to choose an even number of members from each of the 2 groups, and we can at most have 2 girls in our committee. So we could have 2 girls, 1 girl, or no girls at all. So we found all of the possible combinations. We can now add them together. 6 plus 6 is 12, plus 12 is 24, plus another 9, that's going to give us 33, plus 12 is going to give us 45, plus 9 is going to give us 54. So we have 54 total combinations overall for the committees that we can choose. So that's our answer for part number 1. For part number 2, the question is asking us to find the number of combinations of different committees or number of different committees that can be formed if only 1 girl is to be selected for the committee. So that means we need to select only 1 girl out of either of the groups for our final committee. We can actually solve this using this table that we've already drawn. However, you might want to separately draw it or something like that, but we can actually solve it from this table itself. So in this table, there are only 2 possible options out of these 6 total options that we found where we select only 1 girl for the committee. And they are this option and this option. We can see in the first option we have 0 girls from group 1 and 1 from group 2. In the second option we have 1 girl from group 1 and 0 girls from group 2. So therefore, these 2 are the options where we select only 1 girl for the overall committee. The rest of them are from the case where we select 2 girls for the committee. You can see 1 plus 1 is 2, 0 plus 2 is 2, 1 plus 1 is 2, and 2 plus 0 is 2. So therefore, if we drew this table like we did here, for the second answer, we could make an argument from the first answer saying that in the table these are the only 2 possible options or something like that. However, we could derive it organically as well. For my purposes, however, and for exam purposes, it should be accepted for you to simply say something about the table that you've already drawn if you drew a table already. If you haven't, of course, you need to draw it from scratch or something like that. But if you have drawn a table like this, then you could write something like, from the above table, the 2 options where we have only 1 girl for the committee are that option and that option. So the total number of combinations is going to be coming from these 2 only. As we found above, the total number of combinations for this first option is going to be 6, and the total number of options for this second one, the total number of combinations, is also going to be 6. So therefore, the total number of combinations of committees for which we have only 1 girl appointed is going to be the sum of these 2 options, which is going to be 6 total combinations for the first one, plus 6 total combinations for the second one. So our answer is going to be 6 plus 6, which is 12. So there we go, there's our answer. We have answered an A-level combined mathematics paper 1 part B question. Let's move on to our second and last A-level past paper question. Here we have the 2020 A-level combined mathematics paper 1 part B question 12A. In this question it says 6 mangoes and 4 oranges are to be distributed among 8 total students such that each student received at least 1 fruit. So that means that no student is left with 0 fruits. Going down, we can see the question is asking us to find the number of different ways in which, and then we have 3 questions. The first question says, find the number of different ways in which 6 students get 1 fruit each, and out of the remaining 2 students, 1 gets 2 mangoes and the other gets 2 oranges. This means one guy gets 2 mangoes, 1 gets 2 oranges, and the other 6 can get random fruits from what's left over. The second question says, find the different number of ways in which 7 students get 1 fruit each and 1 student gets 3 mangoes. So we can select one guy to get the 3 mangoes and everyone else has to share all the fruits that are left over. And lastly, the question number 3 says, find the number of different ways in which 7 students get 1 fruit each and 1 student gets 3 fruits. The distinction between the second and third question is that the second question specifically says that the student needs to get 3 mangoes. The last question says that the student just needs to get 3 fruits. So here, the 3 mango case is a subset of the 3 fruits case. In the 3 fruit case, we could get 3 mangoes, but we could also get other options that are not included in the 3 mango option. Those are that the 1 student gets 3 fruits, could get 2 mangoes and 1 orange, 1 mango and 2 oranges, or even 3 oranges. So what we have to do in the third question is expand on the second question with the other 3 possibilities for getting 3 fruits. So let's start solving with the very first question. 6 students get 1 fruit each, and out of the remaining 2 students, 1 gets 2 mangoes and the other gets 2 oranges. So in order to solve this, we first need to figure out what our distribution is, how we are going to be giving these things, and how we can mathematically find the way that we are going to be giving them. So here we can see that one guy gets 2 mangoes and one guy gets 2 oranges, and everyone else, which means the rest of the people do not have any special relationship that between each other, like they can be taken as being exactly the same, but one guy is special in that he gets 2 mangoes, another guy is special in that he gets 2 oranges. So selecting the guy that gets 2 mangoes and selecting the guy that gets 2 oranges is a special operation. It's different from the other 6 people who just get all the fruits that are left over. This guy is guaranteed to get 2 mangoes and this guy is guaranteed to get 2 oranges. So let's try and figure out how many different ways one person could get 2 mangoes and another person could get 2 oranges. Since we know he has to get 2 mangoes and this other guy has to get 2 oranges, we could think of it as the teacher selecting a student to get 2 mangoes and also selecting a student to get 2 oranges. In which case it's kind of more forced, in that instead of finding every possible way that this could happen as like some random distribution, we could instead consider the teacher to be selecting a specific person or choosing a specific person out of the crowd of 8 people to get the 2 mangoes and another person out of the crowd to get the 2 oranges. So therefore, for our answer, what we're going to do for answer number 1 is consider the different number of ways in which some guy could be selected to get the 2 mangoes. So we're going to write down here ways that a person to get 2 mangoes can be selected. So how many different ways are there? Well, if we have 8 total people and we need to choose one of them to get the 8 mangoes, so therefore the number of different ways in which we can choose one person is 8 choose 1. We could also say it's simply 8 because there's 8 total choices. We don't have to go to the choose function, but it's 8 choose 1. 8 choose 1 is 8 factorial divided by 1 factorial times 7 factorial, which is going to give us 8. So therefore the different number of ways that we can select a person to give mangoes to, the 2 mangoes to, is 8. Now once we give the 2 mangoes to that guy is no longer any of the other people. He is not one of the people who gets 2 oranges and he's not one of the people who gets only 1 fruit. So therefore, this guy is now eliminated from our original set of 8 total students because he's one of the students that gets the 2 mangoes. So that means he's not one of the students that does anything else. So now that he's gone, there's only 7 students left over for us to randomly choose from. Let's say that the teacher, once again, similar to how the teacher chose one of the people to get the 2 mangoes, chooses another one of the people to get the 2 oranges. Importantly, this person that gets the 2 oranges is not the person that gets the 2 mangoes. So therefore, he has to be chosen from the remaining 7 people. So then, if we consider different ways that a person can get, let's say gets 2 oranges can be selected. We are selecting from the total number of 7 people that are left over after we selected the one guy to get the 2 mangoes. So therefore we have 7 total choices. We have to choose one, so therefore 7 choose 1, which is going to be just 7. So the different number of ways we can choose the second guy that gets the total 2 oranges is going to be 7. So now since these 2 events are independent of each other, different ways that we can choose one guy to get the 2 oranges and the other guy to get the 2 mangoes is going to be 8 times 7. But now that we've done this choice, we have 6 people left over. These 6 people need to be given oranges and mangoes. According to what we had earlier at the beginning, we have 6 mangoes and 4 oranges, which means we have 10 total fruits. If 2 of these are given to one guy, as in 2 mangoes are given to one guy and 2 oranges are given to another guy, we have 4 mangoes and 2 oranges left over, which means we have 6 total fruits left over. If at least one student gets 1 fruit each and we have 6 total students left over and 6 total fruits left over, we can say definitively that each student must get only a single fruit, and exactly a single fruit. As in, we have 4 mangoes and 2 oranges left over. From the 6 students, every one of them, in order to get at least 1 fruit, must get exactly 1 fruit. So out of the remaining 6 students, which I'm going to label, represent simply as 6 squares like this, we need to give 2 of these guys the 2 oranges, and the rest of them will be getting mangoes. Or conversely, we need to choose 4 of them to get the mangoes and 2 of them to get oranges. Now importantly, crucially, since each of them gets exactly 1 fruit, if we choose 2 people to get the oranges, we know that the rest of them are guaranteed to get the 4 mangoes. So because of this, we don't need to check how many different ways we can give the mangoes and then check how many different ways we can give the oranges, since if we give the oranges, then the remaining people are definitely going to get the mangoes. So there's only one way to give the remaining people the mangoes, and that is to give each of them exactly 1. We could write this like this as well, saying that out of the 6 total people, we need to choose 4 of them to get the mangoes. So I could say ways to choose 4 people to get mangoes equals to 6 choose 4, since we need to choose 4 of the 6 people to get the mangoes. And for the remaining people, once we give the 4 mangoes away, we only have 2 oranges and we only have 2 people left to give them to. So therefore, the ways to choose 2 people to get oranges is equal to the 2 people that we will choose from, choose 2, since we need to choose 2 people out of those 2 people to give the oranges to, which is 1. So it doesn't really matter, as I said, but we could write it like this even though we know that it doesn't really matter. So now we have 6 choose 4. 6 choose 4 is going to be 6 factorial divided by 4 factorial times 2 factorial. 6 factorial divided by 4 factorial is going to give us 6 times 5, since all the other terms cancel. 6 times 5 divided by 2 factorial is going to be 6 times 5 divided by 2, which is going to be 3 times 5, which is going to be 15. So therefore this answer here is 15, and 2 choose 2 is going to be 1. Now then, once all of these events were completed, the following events were independent of the previous events. Due to that, this 7 choose 1 is independent of this 8 choose 1, and therefore, if we want to find the total number of combinations in which both of these events occur, we can simply multiply the numbers. The same thing with these two, since the different ways to choose the 4 people to get the mangoes is independent of who gets the 2 oranges and who gets the 2 mangoes. So therefore, the total different number of combinations of different ways in which 6 students get 1 fruit each, and out of the remaining 2 students, 1 gets 2 mangoes and the other gets 2 oranges, is going to be the product of all of these numbers. We have 8 different ways for the first guy to be chosen to get the 2 mangoes, 7 different ways for the second guy to be chosen to get the 2 oranges, 15 different ways to choose the 4 people to get the mangoes, and only 1 way, given that we already gave those 4 mangoes, to choose the people to get the oranges. So therefore, the answer is going to be the product of all of these. So 8 choose 1 times 7 choose 1 times 6 choose 4 times 2 choose 2, which is going to be 8 times 7 times 15 times 1, which if you work it out, we can see this 15 times this 8, we can simplify this down to, we can simplify it slowly if you can't follow it. If we multiply one of the 2's from this 8 with this, we get 30, multiply by another 2, we get 60, multiply another 2, we get 120. 120 multiplied by 12 is going to be, so 120 multiplied by 7 is going to be 700 plus 140, which is going to give us 840. So the answer here is 840 ways. There are 840 unique combinations of different ways for us to give 6 students 1 fruit each, and out of the remaining 2 students, 1 gets 2 mangoes and the other gets 2 oranges. Now, it is important to note that when we did this calculation, our assumption was that all the students were unique from each other. This is a common assumption to do when you're dealing with people, since people tend to be unique. You tend to never have 2 people that are identical to each other. The only way that could happen is if the 2 people are literal clones of each other. So, for purposes of counting people, we must use the fact that people tend to be unique and assume that all the elements in our sample set, meaning all of these 8 people, 8 students, are unique from each other. So that's the solution to the first question. Let's now move on to the second question. The second question asks us to find the different number of ways in which 7 students get 1 fruit each and 1 student gets 3 mangoes. So once again, we could think of this rather than random choice where 1 student gets 3 mangoes and such. We could think that the teacher specifically chooses 1 student out of the 8 to get the 3 mangoes and the rest of them randomly get whatever is left over. So once again, using that logic, if we go down here and solve question number 2, we can say that ways to choose the person to get the 3 mangoes, which is the special case, is going to be the different number of ways that we can choose one guy from 8 total people, which is going to be 8 choose 1, which is going to be 8. So the different number of ways we can choose the one person who gets the 3 mangoes is 8. So now let's suppose we give him the 3 mangoes. If we give him the 3 mangoes from our original starting point, we know that we had 6 mangoes initially. If we give him 3, we have 3 mangoes left over. So we have 3 mangoes left over. We also have 4 oranges left over. So in total we have 7 fruits left over, which consist of 3 mangoes and 4 oranges. The question is now asking us to divide this among the remaining 7 students each. So each of them, if each of them gets at least 1 fruit, each of them must once again get exactly 1 fruit. So all 7 students are kind of boxes in this case, where each of these boxes must get exactly 1 fruit. So once again, we have to do the same thing that we did earlier, except this time the numbers are different. This time we have 3 mangoes and 4 oranges to give to these remaining 7 students. Once again, we have to apply the logic where if we choose 3 people to get the 3 mangoes, the other 4 people are guaranteed to get the remaining 4 oranges. So therefore, we don't actually have to calculate that. If we do calculate it, of course, and we use logic correctly, we will see that the total number of ways that we can choose the remaining 4 people to get the 4 oranges is going to be 4 choose 4, which is 1. So therefore, it doesn't matter. But we'll do it anyway just for the sake of mathematical consistency. So the ways to choose 3 people to get the mangoes is going to be the different number of ways that we can choose 3 people out of a set of 7 people to get the mangoes, which is going to be 7 choose 3. We'll evaluate that later. For now, let's go to the next line where we need to figure out the total number of ways that we can give the remaining 4 people the 4 oranges. So the ways to choose the 4 people to get those 4 oranges is going to be the different number of ways that we can choose from the 4 remaining people to get 4 oranges, which is going to be 4 choose 4, which is going to be 1. We can see this is going to be 1, and any n choose n is going to be 1 by the fact that it is going to evaluate to 4 factorial divided by 4 factorial times 0 factorial, which is just going to give us 1. As for the 7 choose 3 is going to be 7 factorial divided by 3 factorial times 4 factorial. 7 factorial divided by 4 factorial is going to be 7 times 6 times 5, and 3 factorial is going to be 6. So therefore our answer is going to be 7 times 6 times 5 divided by 6, which is going to be 7 times 5 or 35. So therefore the answer here is 35. So we have 35 different ways to choose the 3 people to get the mangoes, and the remaining ways that we can choose the remaining 4 people to get the 4 oranges is exactly 1. Given all of that, the different number of ways that we can choose the person to get the 3 mangoes left over is 8. Once again, since all of these events are independent of each other, meaning that no matter who we choose to get that 3 mangoes, the remaining number of people will always have this many ways to choose the 3 people to get the mangoes. Due to this, we can use the fundamental theorem of counting and say that the different number of ways, total combinations, is going to be the product of all of these individual combination steps, which is going to be 8 choose 1 different ways to choose the guy that gets the 3 mangoes, times the 7 choose 3 different ways to choose the 3 people to get the remaining mangoes, times the 4 choose 4 different ways that we can do to find the remaining 4 people that get the 4 oranges. And if we multiply all of these together, we have 8 times 35 times 1, and 8 times 35 is going to be 4 times 70, which is going to be 280. So therefore the answer here is 280. There are 280 different unique ways in which we could select one guy to get the one guy out of the 8 to get the 3 mangoes, and the remaining people to get all of the remaining fruits. Once again, I should iterate the fact that all of these people that we are considering here are considered to be unique from each other. Moving on to the third and final question. The third and final question says, find the different number of ways in which 7 students get 1 fruit each, which is the same setup as earlier, but now 1 student gets 3 fruits. So as I discussed earlier, if 1 student gets 3 fruits, there are 4 different ways in which he could get those 3 fruits. So let's go down, and what we're going to have to do for this question is to consider all 4 of those cases separately and solve for each of them and add those total number of combinations together. So doing so, if we consider question number 3, the different number of ways that the guy can get 3 fruits, which I'll actually write, ways to get 3 fruits is to either get 3 oranges, 2 oranges and 1 mango, 1 orange, 1, I should actually make this orange O look separate from the rest of, otherwise this looks like 30 and this looks like 20, so I'll put like a line through it. That way you know it's a O, not a 0. So we have 1 here, and 1 orange and 2 mangoes, or the fourth possibility of getting 3 mangoes overall. So these are the 4 possible cases. In these kind of questions, it might be handy to label these cases. So I'll call this case 1, I'll call this case 2, I'll call this case 3, and I'll call this case 4. So in this case, we're going to be having to handle each of these cases individually, solve for the total number of ways that we could have combinations of different students, given that we have case number 1, given that we have case number 2, and so on, and then add all of them together. So let's start solving for each of these. We could do this in a table, and that would probably be the most handy way to do it, since if you don't do it in a table, it might be messy and your solving might be difficult for you to read and for the examiner to read as well. So let's quickly mark up a table and start solving these 4 cases. So there we go. We have the 4 different cases in a table. Let's now consider each of these cases individually and consider what's going to happen with the distribution of fruits. For case 1, we have 3 oranges given to the person. If that person gets 3 oranges, then considering what we had initially, which was going to be 6 total mangoes and 4 total oranges as given in the question, we are going to be left with 6 mangoes and 1 orange to give to the remaining students. So if we go down here, what we're going to have is 1 student getting 3 oranges, so 3 oranges, and the remaining, now this doesn't have to be too descriptive, you can write whatever you want in here because this just needs to be understandable to you. So we have 3 oranges given to the main guy, and then we have 6 mangoes and 1 orange given to everyone else. Now then, considering this situation, the different number of ways to choose the guy to get the 3 oranges is of course going to be 8 choose 1. We need to multiply that by the different number of ways in which we could give the remaining 6 mangoes to the leftover guys, which is going to be, we're going to have 7 people left over, and we're going to choose 6 of them. So it's going to be 7 choose 6. 7 choose 6, or we could choose the one guy to get the orange, in which case it would be 7 choose 1, which is going to be the same exact value. And as for the rest of it, actually that's it. There's nothing else. We could write the different number of ways to give the remaining mangoes, which is going to be 6 choose 6. And if we write that down, now we can find the answer. 8 choose 1 is 8, 7 choose 1 is 7, and 6 choose 6 is 1. Simplifying this down, we can see the answer for this case 1 is 56. Now considering case 2. In case 2, 2 oranges and 1 mango went to the first guy. So here we have 2 oranges and 1 mango going to the first guy, and the remaining people get 5 mangoes and 2 oranges. Since we had 4 oranges originally, if we give 2 to the first guy, 2 will be left over for the remaining people. If we had 6 mangoes initially, 5 will be left over for the remaining people. Now, considering the situation, the different number of ways in which we could give 2 oranges and 1 mango to the singular guy is just going to be the different number of ways in which we can choose the guy to give that to. So therefore, it's going to be 8 choose 1. Now once we give those 2 oranges and 1 mango to that guy, we have 5 mangoes and 2 oranges left over to give to 7 people. So we need to choose either 5 people to get the 5 mangoes, or 2 people to get the 2 oranges. if we choose, let's say, the 2 people to get the 2 oranges, we have 7 choose 2. Once we give those 2 oranges away, we have 5 people left over that need to be given 5 mangoes. So therefore the total number of choices for those people is going to be 5 choose 5. If we evaluate all of this, 8 choose 1 is going to be 8. 7 choose 2 is going to be 7 factorial divided by 2 factorial times 5 factorial. 7 factorial divided by 5 factorial is going to be 7 times 6, since all the other terms cancel. 7 times 6 divided by 2 factorial is going to be 7 times 6 divided by 2, which is going to be 7 times 3, which is going to be 21. So multiply by 21, and 5 choose 5 is 1. So the answer is going to be 8 times 21, which is 160 plus 8, which is going to be 168. For the third case, we need to give 1 orange and 2 mangoes to the first guy, which means the remaining people are going to get, if we have 6 mangoes initially, we are going to have 4 mangoes to give and 3 oranges to give. So this is our distribution for the third case. In the third case, the different number of ways that we can choose the special guy who gets the 3 fruits is going to be 8 choose 1. Now that we've done that, we have 4 mangoes and 3 oranges to give. The different number of ways we can choose the 4 people to get the mangoes or the 3 people to get the oranges is going to be 7 choose 3. And once we give those fruits, we're going to have 4 people left over to whom we need to give the mangoes, which is going to be a 4 choose 4 situation. And now that's it. So if we evaluate this, 8 choose 1 is 8. 7 choose 3 is going to be 7 factorial divided by 3 factorial times 4 factorial. We actually solved this earlier, but we'll solve it again. 7 times 6 times 5 is going to be 7 factorial divided by 4 factorial. And we divide that by 3 factorial. 3 factorial is 6, so what we need to do is to find 7 times 6 times 5 divided by 6, which is going to be 7 times 5, which is going to be 35. So multiply by 35. And then multiply by 1 for the 4 choose 4. This is going to be 8 times 35, which is going to be 4 times 70, which is going to be 280. So the answer here is 280. For the very last case, we need to give 3 mangoes to this guy, and once we give the 3 mangoes, then we give the remaining 3 mangoes and 4 oranges to this remaining people. Now once again, we can actually evaluate this, or we could go back and realize that the case where the one guy gets 3 mangoes and the rest of them get 3 mangoes and 4 oranges is actually the case that we figured out in question number 2. The ways for the different one person to get 3 mangoes is exactly what we're doing in this case here. So we could say found earlier or something here, found earlier in, we could say Q2, right? So that way people know, the whoever's marking this knows that we found it early in Q2. And we can say it's equal to 280 because that is what we found in the previous question. So now we have the 4 different combinations that we could have in each situation where the one person gets 3 fruits. When the one person gets 3 fruits, they either get 3 oranges, 2 oranges and a mango, 1 orange and 2 mangoes, or 3 mangoes. Adding all of those different combinations up, we can see that our total sum is going to be 56 plus 168 plus 280 plus 280. 280 plus 280 is 560, plus 56 is going to give us 560 plus 56 is 610, 616, and 616 plus 168 is going to be 716, plus this is going to be 776, plus an 8 is going to be 784. So we have 784 different combinations for giving one person 3 different fruits and giving the rest of them any fruits that are left over. So then, that's going to be the end of this video. We've done 2 example questions and we've also covered all the different ways that we could have questions regarding choices, how to do choices using the choose function as in combinations. We've also discussed what to do in the case where you have duplicate elements, in which case for permutations, if you are taking the total number of permutations, you just need to divide by the total number of duplicates, factorial. And in the case where you have subsets that you're trying to create, you actually need to find the different number of subsets that you can create, where each subset may have a different number of duplicates within it, and for each of those subsets you need to solve it separately and then add them all together. There's no real easier way to do it. You kind of have to do it for every single case. So that's going to be it for this lesson. We're going to end it there. If you have any questions, post them down in the comments down below. If you have any requests for future videos also, post them down in comments. Thank you for watching and goodbye.